Okay, good afternoon, students. Welcome to the today's class. Today we would like to look at lecture number 12, shift registers. So it's very important. That's the reason why I have taken a separate session for this, and we'll go for the remaining part of the counters in the next class. Okay, fine. So let us recapitulate what we have seen in the last class. So basic theory, basic design theory. Theory on resistors. Okay, so registers are used to store a set of bits. It is possible to configure the registers as a shift register, either left shifting of the information or right shifting of the information. That means, for example, you have a 4-bit registers, 1, 2, 3. 4-bit register means 4 flip-flops are required. For example, we have a Q0 position here. This is a Q1, this is Q2, this is Q3. So therefore, this is Q0, for example. Okay. Now, if you want to perform the left shift of operation, what we can expect? The left shift of operation, expect that 2, 3, 4. It requires a serial in data. Okay. It is coming from the outside. Then Q0 is occupied here. Q1 is occupied here. Q2 is occupied here. Q3 will be disappear. So this is what left shift operation. Okay. How we have to connect all these things also we have seen in the last class. For example, if you want to perform a right shift of operation, what we need to do is that serial in data have to apply here, and here Q3 is occupied here, Q2 and Q1. Okay, this is what we normally call it as right shift operation. Agreed? Fine. Now, how the connection between the flip-flops also we have seen. Now, our objective is that, we have already seen the connection among them. Connection among flip-flops to configure as a shift register. Okay. Okay. Best what I want to do here is that first of all, I would like to write the structural modeling for this one. Structural modeling. Later, I'll go for the behavioral modeling. Best behavioral modeling also we would see. Okay, like that. So we already know about the right shift operation or left shift operation with the help of flip-flops. Okay, this is the one flip-flop. The same flip-flop we need to use it for 3 times because I would like to design 4-bit shift register. Okay, if you want to perform a shifting operation, you should remember that it will be configured as serial in, serial out data. Okay. Now I want to see. I want to apply. This is, for example, what we can call. This is a D3, for example, Q3, D2, Q2, D1, Q1, D2, sorry, D0, Q0. Okay, so what it says that we have to apply the serial in data at this point, serial in data, and we would like to take the serial output data at this point. Okay, now the connection between these things is something like this. Okay, it is very important to note that every flip-flop has got a negative edge triggered clock signal. Okay, it is called a clock signal. It is mandatory to know that every flip-flop has got a reset signal as well. Every signal has got a reset signal. Every flip-flop has got. Okay, so this is what actually the inside of the shift register. So what is the top level module for the shift register now? The shift register is something like this. Okay, the shift register is something like this. We're having only the serial in data. We will get the serial out data, serial in and serial out. We have a reset signal. We have got clear terminal, sorry, clock signal. Okay, what is the inside of this one is decided by this diagram. Okay, unless otherwise, if you are not say, if you are saying that what type of, how many number of, what is the size of the register, we don't know what is the how much shifts it can perform. So just to randomly we have to check it there. But actually our requirement is that we want to perform, or we want to design 4-bit shift register. 4-bit shift register. So we know very well about structural modeling. What is the structural modeling says that if you want to write the structural modeling, it uses the same type of D flip-flop. Okay, what is the D flip-flop we have seen? So let us copy from the previous classes the D flip-flop where I have written memory element D flip-flop. No, J flip. Yes, this is what. Yeah. Usually we prefer to write asynchronous reset only. Okay, so I copy this one without wasting my time. I want to use this one. Okay, first of all, whenever we want to write the structural modeling, what is the basic component is there in that one? I need to check accordingly. So yeah, accordingly I need to follow. Okay, synchronous clock that I have given here, I think I want to remove all the unnecessary parts here. Okay, it's not necessary. I would like to use negative edge reset signal. Okay, negative edge of clock signal and negative edge of reset signal. Okay, okay, if not of RST, I think I need to write properly. If not of reset, Q must be 0. What is happening here now? What is the size of the registers that I am talking about? No, only single bit information I need to talk about first of all. Later I will talk about the remaining things. Okay, the clock and negative edge of reset, and this is happening. Fine, that's good. Okay, this is what actually a D flip-flop. But the structure says that it needs 4 such type of flip-flops are required. Am I right? Okay, so I think better I have to take this entire thing, copy. I want to paste it here. Okay, so my top level module is look like something is a module shift register shift underscore shift right, RIGST right. This is the name I'm giving. SIN clock reset yes out. All are small letters only. Please remember that I have written all are small letters only. Okay, so out of all these things, inputs are SIN clock reset signal. Output is, since structural modeling, we don't want to write the register data type. Just I can write only S out only. Okay, that's it. Nothing else. Now I have to call how many times? 4 times I need to call this flip-flop, right? This flip-flop I need to call 4 times. copy, and I want to paste it here. Okay, 1, copy, and then paste here. Second flip-flop, third flip-flop, and fourth flip-flop. Agreed? But we need to write its name of the modules are M1, M2, M3, M4. That means that I am treating this is a M1, this is M2, this is M3, this is M4. Okay, now what is the necessary input and output for this one? For the first one, the input is actually D3 is connected to SIN. Okay, I need to remove this one. I need to write SIN. Okay, SIN. What is the RST signal? RST is same name I have used. Clock also I have used the same name. What about Q? Did we mention any name for that one? No. So let me call this is Q3. This is Q2. This is called Q1. The last one is S out. Okay, this is called Q3. Q3. Next, this is called Q2. This is called Q1. What about the last one? Last one is S out. S out. But here also it is very important to note that what is the DN signals for all everything. This is here actually Q3. This is Q2 generated from previously. This is Q1 generated from previously. That's it. But Q1, Q3, Q2, Q1 are internal to the circuit. Therefore, I would like to write wire Q3, Q2, and Q1. Agreed? Now I want to end this module. Okay, that's it. Okay, I hope you understood the concept, whatever I have written here. So this is actually the module that is necessary in the structural modeling, and just I have followed the top level module. Okay, so what is the test bench for this one? I'll give you the input test vector, and please try to write the test bench for it. Okay, okay, test bench. What are the things required here now? Please remember that what things are required. Copy and paste it here. What things are required? We need SIN is required, clock is required, reset is required. Okay, okay. So better I will consider previously what is the pattern that I have taken. Not like this one. I think this one I have written. Yeah. I will take this input signal. Copy. I want to paste it at this place. Okay. What is missing here? SIN is required, right? SIN we have to apply the SIN initially, that is low. Initially we want to make that is low, and from this point I am applying logic 1 there. Throughout this one, logic 1 I'm applying. This is called SIN. Okay, so please try to write a test bench for this with these 3 signals. We know how to write the test vector for this test bench for it. Okay, now fine, that's good. What about shift right operation? Okay, so I would like to discuss about shift right operation. Sorry, shift left. Shift left register. Before going to the shift left operation, first of all, let me write the behavioral modeling for this one. Okay, so it's a good idea for that. Then shift right using behavioral modeling. Behavioral modeling. Okay, so behavioral modeling requires only the logic inside of this one. It doesn't require what is the inside of the circuit. Okay, so we don't bother about it. Okay, so this one is the top level module, and the theory is something like this. Okay, so shift right operation means this is what has to happen. Copy and then paste here. Okay, so what I'm trying to do here is that whenever I have a reset signal, clock signal, SIN signal, and I want to calculate S out. So that means that S out will be calculated later on, but internal to the circuit is also we should know very well. Okay, so that means we would like to know what is the Q values, Q3 to Q0. What will happen? And here is actually Q0 is actually S out only. Okay, fine. Let us see here. If we have a negative edge triggered negative edge RST, irrespective of the clock SIN, what is the value of all these things? All these things are equal to 0. And what about S out? S out is actually Q0 only. So that's what we can see. See, the problem is that if you are initializing the resistor with all zeros, okay, even if you are shifting something, we don't find anything. Okay, so but since we have a SIN signal, even if you are initializing the content of the flip-flop with all zeros, it won't get any kind of problem. That's the reason why this is what is happening. Now it is not there. For other cases of the RST, we have a negative edge of the clock. If Cn is equal to 1, for example, Cn is equal to 1, for example, then what will happen? The Q3 is assigned by logic 1. This one is going here. This one is going here. This one is going here. Okay, so therefore, according to this one, we will get a 0 at this point. Q0 is actually assigned to S out, right? Now again, for other cases of this thing, apply the negative edge trigger. Same one will apply here. Okay, then what will happen? This one is occupying at this position, and this one is actually from here, and that is the way it is moving to the next stage. Okay, what about other cases? For other cases, for negative edge of the clock, when we apply another one is observed here. The one is previously Q3 to Q1, Q2 to Q1. This is 0. For other cases, the last one, if you apply the negative edge, if you apply 1, 1, 1, 1 will be there. That is 0. Here also 0. Okay, if you want to see the content of all the flip-flops, how many clock pulses are required? How many clock pulses? 1, 2, 3, 4. Since it's a 4-bit register, means 4 clock pulses are required to completely take the information out of the flip-flops. Okay, so if you are not interested to use the initializing with all zeros, you can put any data. Okay, apply all the logic 1 in the SIN, or maybe all zeros in the SIN. It doesn't matter. But thing is that whatever the content of the flip-flops are there, that must be coming outside of this. Okay, so this must be the functional table for a flip-flop, sorry, for a resistor. So with this one, let us write a Verilog program. Okay, what we observe that module shift underscore register. I would like to write a shift right. We have SIN, we have a clock, RST, S out. Okay. Now the inputs are SIN, clock, reset. Output is S out. Okay. Output is S out. So what I want to try to do here is that always statement I need to use. Okay. Always for every negative edge of RST, comma, negative of clock. Okay. These things must be user defined one. This is also user defined one. Okay. If this is the case, let us write begin and then here. So what is the logic here now? As we know that very well, we want to initialize the content of the flip-flops, right? With the negative RST. Then what about the Q value? All the content of the Q is equal to 4-bit of all zeros. See, what I'm trying to do here is that Q is not there in the top module. Q is not there. It is inside of the circuit. Okay, therefore what I have to do, Q is available inside of the always block means we have to write instead of a wire, we have to write a register data type. We have to write register data type. Register 3 down to 0 of Q. Agreed? Okay, I have filled all the content of this one. Now what will happen? See here, else, if it is not the case, else, let us begin here. Begin and here. So if that is not the case, Q of 3 is assigned by, so very, very important thing that I'm writing here. So it is called non-blocking statement. Q3 is assigned by, of course, Q3 is actually, you should not write like this. Instead, we need to write this one is Q of 3 is actually Q of 2. That is what it must be go. And Q of 2 again go by Q of 1. And Q of, no. What we have to do, Q of 3 is assigned by SIN, right? SIN. Okay. Similarly, Q of 2 is assigned by Q of 3, right? It's Q of 3. Q of 1 is assigned by Q of 2. Okay. Q0 is assigned by Q of 1. Okay, this is how the shifting has been performed. This is how the shifting has been performed. Okay. This is how the shifting has been performed. One important point is that once the shifting is completed, what I want to do is that whenever I find assign statement, I will use. So what is this for assignment statement? Assign S out is equal to whatever the Q of 0 is there, that Q of 0 must be assigned to this one all the time it is happen. Okay. Finally, I need to write end module. So here the assignments are as follows. So these assignments are called blocking assignments on top. What we can call it as blocking. Sorry, non-blocking assignment. Non-blocking assignments. So this point we will see later on what is exactly this one. But if you're using only equal, then this is called blocking assignment. Blocking assignment. blocking assignment. So for realization of the sequential designs, it is better to use non-blocking assignment than blocking assignment. Okay. So this is the one approach, be completely based on the logic orientation. Okay. Okay. I didn't bother about what is the inside of the circuit, just the logic I have followed. Just I have followed the logic. Agreed? Okay. Most in better way also we can do it like this. It is also do the thing in most but easiest way as follows: alternative method. Alternative method. Okay. So what is the alternative method for this behavioral modeling? Just we follow this one. So the alternative method is as follows. Okay. What we observe that, for example, we have this is what the output resistor, right? This is what the output resistor. As we know that here is actually filled with SIN, and this one is Q3. This is called Q2, and this is called Q0. This is happen for every negative edge of the clock signal, right? Of course, apart from the reset signal, this is what happening. Okay. Therefore, what I can do here is that instead of writing this entire statement something like this, else statement something like this, okay. So instead of writing the else statement something like this, I'll follow in this manner. Else Q is assigned by for every negative edge of the clock signal, the MSB bit is filled with the SIN, and the remaining portions Q of 3 down to 1 is possible to use. So concatenating the bits here, you see here, just only the concatenating of the bits. That's what happening here. So here what we observe. So the first bit is actually SIN, right? The remaining portion what we have done. So Q3 to, sorry, it's Q1. So I'm extremely sorry. This is called Q1. Q3 to Q1 must be occupied for the remaining portions. That means this is called Q3, Q2, Q1, Q0. Okay. Therefore, the Q3 is assigned by SIN, Q2 to Q0 is assigned by Q3 to Q1. So this is the way that we can write. This is the simplest way that we can write the Verilog program for this. A single statement is sufficient. So what is this one we can call it as? It is called concatenation operator. It is called concatenation. Concatenation operator. Concatenation operator. Okay, it's combined the thing. So we discussed about this point previously also. Okay, this is the simplest way that we can do it. Agreed? I hope you understood the concept here. Okay, can you do the same thing for the left shift operator? I hope the concept is very clear. You are in a position to do this one also. Okay, so better I'll take this code. Okay, let it be like that one. Okay, so this is what we can write. Okay. Okay. Fine. Let's go for the bidirectional shift register. Okay, so shift writing and shift left operation has to do. So it is, I'm giving you exercise, write the structural modeling for it, structural modeling, because already I told you in the last class, what is the basic idea? Structural modeling of bidirectional shift register, bidirectional shift register. Huh? Okay, so you can do it in your home. It's a homework. Now I would like to do the behavioral modeling here. Okay, so behavioral modeling of bidirectional shift register, BSR, bidirectional shift register. Okay, very simple. Okay, we have a block diagram here in this way, for example. Okay, so the information should go from inputs left hand to the right hand side or right hand side to the left hand side. SO. It is possible only by using one enable signal. By using only one enable signal, it is called shift control or shift enable. SC or shift control or shift enable also we can write it there. Okay, so don't forget about that. We have a clock signal, we have a reset signal, reset and clock signal. So bidirectional shift register. Okay, so I should mention what is the size of this one. It is a 4-bit. It's a 4-bit. Can we write very easily? Okay, so I'm using the same concept, nothing else here. So I'm going to use the same concept here. Okay, copy. I want to paste it at this place. Okay, so what is the modification that I have to do here? What is the modification that I have to do is that. So the modification is that I have to include SI and S out. I have written right. So better I don't want to change the names SIN, S out. Okay, and the clock and reset, everything is same. Now I would like to introduce the next one is called SC, shift control. SC is the shift control. Okay, SC will be the shift control. So I can place the shift control at this point also, right? SC. Okay. For every positive edge of the, for every negative edge of the reset signal, the contents must be clear. For every negative edge of the clock signal, what has to happen? For every negative edge of the clock signal, depending upon SC, it has to perform the right shift operation or it has to perform the left shift operation. Okay, so that means I have to include an if statement for every negative edge of the clock. So that means I have to go for else if statement. Else if statement. Else if I need to talk about SC, shift control. If the shift control is true, okay, if shift control is true, it has to perform right shift operation. Okay, లేదు. For example, it is not there. Else shift control is not there. For example, else what has to happen? Right shift, left shift operation. What is the left shift operation? Says that anyone from the class? Anyone from the class? Can anybody tell me what is the answer for this? For the left shift operation, right shift, I told you. You can type it on the chat box or you can speak also. Students respond. What will be the case? Here, exactly. Voice is audible or not? Hello, students. My voice is clear? Or we are getting very low voice. Yeah, thank you. Okay, that's true. One of our friend has suggested me to write something like this. It is Q of 2 down to 0 with SIN. Very good. Thank you very much. So I sorry, I forgot to write here is the semicolon. Here also I need to write semicolon. I think previous one also I forgot, I think so. Yeah, I forgot to write the semicolon here. Please put a semicolon there. Okay, that's it. That is the thing here actually, right? So this is the begin and something. So one point we have to remember, S out will be actually Q of 0 is meant for, this Q of 0 is meant for right shift operation. What about left shift operation then? What we have to do for the left shift operation? There is an ambiguity in S out, right? We are able to see the S out only for the shift right operation. Are we able to take the shift right operation, shift left operation related S out? Q3 will be there, right? So the question is that you have to think about this one. I'll give you an assignment here also. Think about this one. How do we provide? In this particular case, we are talking about only the Q of 0. Q of 0 is only meant for S out only, for the right shift operation. For left shift operation, what we have to do? Thus, we have to think about it. Okay. So that's select U. Okay, this is the only the ambiguity is there in it. You please try to solve this problem. Okay. Okay, fine. The next one is universal shift resistor. I will give you the today one particular the theoretical aspect here, and in the next class, if possible, I will discuss about the programming. Okay, what is the universal shift resistor? Okay, universal shift resistor. That means it has to perform number one, parallel loading. Parallel loading. It has to do. The second one is it has to perform shift right operation. Shift right operation. Third one is shift left operation. Shift left operation. Fourth one is holding operation. Holding. That means don't want to change the content of the resistors. If any resistor is performing all these things, then it is called universal shift resistor. Okay, this is one of the important resistor generally we use. Okay, that means, for example, see here, I have a resistor, 4-bit universal shift resistor. Consider a 4-bit resistor. Okay, it's a 4-bit USR. Okay, so Here is the content here. 1, 2, 3. So the here is actually Q0 content, Q1 flip-flop, Q2 flip-flop, Q3 flip-flop. So in the first case, what has to happen? Parallel loading has to happen. That means this first position is filled with D3, additional input D2, D1, and D0. This is what happened the first time. That is what parallel loading. What about a shift right operation? For example, I want to perform a shift right operation on this particular Q3, Q2, Q1, Q0. Then what will happen? The serial line data is entered into this one, and this value Q3 is occupied here, Q1 is occupied here, sorry, Q2 is occupied here, Q1 is occupied here. Agreed? This is what parallel loading, PL parallel loading. This is called shift right operation. Shift left operation means it is occupied by Q2. This is called Q1. This is called Q0. Serial in data is occupied here. It is called shift left operation. Holding operation means Q3 means Q2, Q2, Q1, Q0 only. Agreed? So these are the things that we need to remember about the content of the, okay. Okay. Now that means I have a 4 flip-flops. I have got, okay, 1, okay, 2, 3, 4 for here, 4 flip-flops, right? What is the content of the flip-flops now? It is actually D3, for example, D3. It is called D2. It is called D1, sorry, D1, D1. This is called D0. This is a Q, 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 Q. Okay. I think better I need to write inside of this one. It is called D3, Q3, D2, Q2, D1, Q1, D2, D0, Q0. Okay. Now, if you want to perform the parallel loading of operation, what has to do? That means that D0, D3 has to come here externally, D1, D2 here, D1 here, D0 here. This is the one line. Another line is SIN has to come for shifting operation. So SN has to come here, SIN. Okay, sorry, I mean, I'm extended, sorry. SIN here, it is actually Q2. D3 ravali. This is called D3, D2, D1, D0. Similarly, here what we need to know, the second one, SIN here is required, Q3 is required here, Q2 is required here, Q0 is required here. Sorry, Q1 is required here. Sorry, I would write. Okay. Okay, this is called D1, Q2. Okay. In the third case, what will happen? In the third case, the input should be Q2, Q1, Q0, and here is SIN for the third shift left operation. For parallel loading, the holding output requires Q3, Q2, Q1, and Q0. So therefore, this particular line must be assigned by either this input. So this input, first of all, yellow color input has to go so that it is a parallel loading, right? In the second time, this second line has to go. This second line has to go as input to the D3 for shift right operation. In that time, D3 signal, this yellow line signals, and Q2, the other signals should not be there. In the third case, what we have to do, this has to go. This has to go. Okay. Shift left operation. Similarly, in the last case, this has to go. Right. So that means we have to choose a particular logical circuit here. It should allow only one input at a time to this one. That means we need to have one logical circuit is required in order to produce one particular line at a time. Can you guess what is the device can select only one particular line out of n number of input signals? Yeah, simply it is a multiplexer. Simply it is a mux, we can use it here. What is the size of the mux? It's a 4x1 mux. It is a mux. So what is the selection line here now? 2-bit selection line. All the muxes have the same selection line. For example, S0, S1. Therefore, S1, S0 is something like this. 0, 0, parallel loading. 0, 1, shift right operation. 1, 0, shift left operation. 1, 1, holding operation. Hold operation. Right? So this is what actually my universal shift resistor is look like. Agreed? Where you get this? Where you get this Q2, Q3? So Q3 is coming from here. Okay, so you can see that the Q3 is coming here, and it this, and Q2 is actually coming from here to here. S3 is actually coming from outside. Okay, so therefore, without confusion, I would remove that one. So this is actually, it is look like it is simply a universal shift resistor. But do not forget that we have a clock signal, we have a reset signal for everything. Okay, so please try to write the structural modeling for this structure. Okay, and I think better I have to use another color for reset signal without having. Okay, please try to write RST. Sorry, yeah, it may be RST or a clock signal. Okay, so please try to write a Verilog program, structural Verilog program for this universal shift resistor. And we will see the, if possible, try to write the behavioral modeling for this one also, if you know very well. Okay, so we stop here today, and we will see the remaining things in the next class. Okay, thank you very much.